So the simple measurement with grazing incidence X-ray scattering has told us that at the surface or at the interface of the electrode, whether you prepare the material with or without the electrode first, you have a very clear distinction or difference in the structures at that interface. And that actually is what's giving rise to the difference in the performance of these materials. And in fact, from the grazing incidence X-ray scattering measurements, you can also, from the width of the reflection, say something about the crystal size using the Scherrer equation. And if you do this, what you find is that the size scale of the structures normal to the surface are on the order of about 20 nanometers, which again is consistent with the results we have in the past. We've also used near-edge X-ray absorption fine structure analysis. The synchrotron beam is polarized. And so what that allows us to do is place the electric field vector of the X-ray beam in the plane or out of the plane of the sample simply by taking the sample. You have polarization of the electron of the synchrotron beam horizontally. You take the sample. If normal incidence, the electric field vector is in the plane of the film. If I rotate it out, it now places the electric field vector normal to the surface. Now the reason that that's important is that first, bucket wells, it doesn't matter what the orientation is because they're spherical, effectively. But with P3HT, it's not the case. And you can actually look at the orientation of structures right at the surface. And these happen to be two profiles that you get for PCBM and for P3HT pure materials with the electric field vector parallel and perpendicular to the surface. And what you find for the PCBM, which is the blue and the green, you find that they're virtually the same, and that's exactly what you'd expect. But for the P3HT, that's not the case, and you can actually look at the orientation of these molecules right at the surface. And you can also tell from the mixture by looking at the near-edge X-ray absorption fine structure analysis of mixtures. You can tell whether you're getting a segregation of the P3HT at the surface or the PCBM at the surface. And in fact, what you find with the post-annealing case is that you have the segregation of the PCBM at the surface, which is telling you that you're getting this segregation of one component to an interface, and that's very important in terms of being able to understand the structure of the material right at the interface where all the action effectively is occurring in terms of the transport of electrons or holes from an organic material to an inorganic. Now, we've also done dynamic secondary ion mass spectroscopy. Here we've taken the PCBM and we've labeled it with deuterium. And when you do dynamic secondary ion mass spectroscopy, you take an ion beam and you raster it on the surface and dig into the material. So that what will happen is that I start now taking an ion beam and I start to etch the material. And if you have a constant etching or sputtering rate, time corresponds to depth. And what this allows us to do is it allows us to be able to look at the concentration profiles of components normal to the surface. And what we've done is that we spin-coated, we wanted to look now at not just the mixture of the materials, but also how the P3HT and PCBM are interdifusing, because that's important. We're heating material to 150 degrees centigrade. So we take the P3HT, spin-coat it on a silicon wafer. We can take this now and transfer this on the surface of water, allow it to float on water. We take a separate substrate, we can spin-coat a film with PCBM, and then we can take the P3HT and place it on top of this, all right? And so now we have a bilayer of P3HT on top of PCBM, and we actually put a sacrificial layer of polystyrene on the surface. And the reason we do that is that we want the ion beam, when it's etching into the material, to establish a constant sputtering rate so that time now corresponds to depth. And if you do this, there's a stunning result that emerges. All right, we start off initially. We initially start with a situation where we have the black, which is PCBM, deuterium concentration. There's nothing, and then you get into the PCBM layer. P3HT, on the other hand, and this is the sulfur signal. We can see the P3HT, and we get into the PCBM layer. We have nothing. That's simple violet. We take the sample and we heat it, basically for 2 seconds. Each of these layers is about 1/10 of a micron thick, 100 nanometers. After 2 seconds of annealing, what we find is that we have the PCBM has penetrated all the way through the P3HT layer. It's a really fast diffusion process. In addition to that, it's not classic Fichtean diffusion. The profiles that we have is that the concentration profile remains constant, and then it jumps, all right? If we heat it for a little bit further, what we find is that the position of the interface has changed as more PCBM is being drawn into the P3HT, but we maintain this constant profile of P3HT in the PCBM in the P3HT layer. We do see a development of an excess at the surface, and in fact what happens, the PCBM penetrates through the P3HT layer and you get crystallization on the surface. The chair is now left, so that means I have as much time as I want. That's good. So, nonetheless, what happens now is that the model that we're developing is that we effectively have the P3HT, it orders, the PCBM is drawn through the areas that are between intercrystalline regions of the P3HT. And we basically get a very rapid drawing of the PCBM through the P3HT layer, and you get basically a situation whereby you have crystals of P3HT. We have these intercrystalline domains which are effectively amorphous. We have a mixture of PCBM and the P3HT. Now the reason behind this is a very simple, classic polymer physics problem. And the classic polymer physics problem is this. If I take a mixture and one component will crystallize, you nucleate the crystal, and the crystal front will grow. And the crystal front grows, but it is pushing the non-crystallizable material out of the way. And that happens to be the PCBM. So we have the nucleation density, which is of importance, and then we have the growth rate of the polymer crystal and the diffusion coefficient of the impurity, PCBM, away from this interface. And in fact, what will happen if I look at this ratio between the diffusion coefficient and the growth rate, you come out with a length scale. This length scale turns out to be on the order of about 15 nanometers. But that's not the only parameter that's going to be important. The other parameter that comes into play that's of very importance is the nucleation density, so that the more nuclei I have, the smaller will be the ordered regions. Therefore, I have a means by which I can actually control the structure and the morphology of these materials. So I do have to finish. Noda Sensei is getting very anxious. So, you know, what I wanted to do is just to show you a very simple example of a classic system that people didn't understand at all. But by taking the techniques that we now have available, you can actually start to draw a very quantitative picture about what is going on. The folklore of a phase separation of these systems is nonsense. It's really a situation where you have ordering that's driving effectively a seclusion or a sequestration of the PCBM into intercrystalline regions, which gives rise to structures that are on the order of about tens of nanometers in size, which are exactly where you want to be for these systems. This in turn, and I'm going to sneak this one in here, it does give possibility of generating tandem devices, which allows you to take materials that are active in different parts of the solar spectrum and achieve efficiencies that may actually be well beyond the 10% efficiencies that people are currently striving for now. So with that, I would like to thank you for your attention. I would gladly and happily answer any questions if Noda Sensei allows you to do so. Arigatou gozaimasu.
Thank you, Professor Russell. It's quite interesting. Your research result and very precise and mechanism and stress change. So it's very interesting. So because of the time limitation, we have only one or two questions. Any questions? Okay, then about the future of organic robotics and based on your research result, can you expect high efficiency conversion factors?
For one type of material, efficiencies on the order of about 10%, I think are going to say they're cheap. And I think that we'll be able to get, say, up to about 12%. To get beyond that, you're going to have to use structures like this, which are tandem structures, or be able to use some of the concepts that we developed and take a tandem structure like this and break this up into a situation where you have interdispersed materials that are active in different parts of the solar spectrum. You know, I actually think that getting efficiencies of about 20%, I don't think is undoable. If that's the case, then we'll be able to use it more than just for laptop computer cases, which is what Konarku is doing now.
Okay, thank you very much. So again, thanks to the professor.